So there's going to be a big gap here because only the first 5 minutes lecture recorded. So part B is missing, so now we're on part C. But we go on acetic acid followed by, what was this called again? This one, H2CO3? Carbonic acid. What do you know about carbonic acid? You have to have this memorized. Carbonic acid is not stable and decomposes into carbon dioxide and water. In one sense you have to have it memorized, in another sense you don't because you have this acid chart available. But it's good just to have it memorized. What's this one? Hydrogen sulfide or no, sulfuric acid is H2SO4. Hydrosulfuric acid. So this is hydrogen sulfide or hydrosulfuric acid. Because it's sulfide. Sulfides, I erased it, but not the hydro. What's this one called? No, H3PO4 is phosphoric acid. Close. This is a negative charge here. If it's negative charge, we call it an ion, not an acid. This is called the dihydrogen phosphate ion. Dihydrogen phosphate. Phosphoric acid we wouldn't call trihydrogen phosphate. But this one we would call dihydrogen phosphate. This is an ion. And then, what's this ion called? Ammonium. Ammonium turns out to be kind of a weak acid, but ammonium is stronger than this acid. This one's called, two names. Give me two names for this one. Did you guys review your notes from yesterday? I gave you the name for this one yesterday. Hydrocyanic acid, you got it. That's hydrocyanic acid or hydrogen cyanide. What's this one here? We wouldn't call this an acid because it's an anion. So we call it hydrogen carbonate ion, or the old name. Give me the old name for this. It's not really the old name because they still use it. Like for example, if you go buy baking soda, they still use the old name. They call it hydrogen carbonate or maybe you haven't looked at have you ever looked at the ingredients for baking soda? Maybe not. Baking soda, bicarbonate, commonly known as baking soda. And so this bicarbonate, the old name, is much more common than the new name. The new name is sodium hydrogen carbonate. Sodium hydrogen carbonate versus sodium bicarbonate. Sodium bicarbonate is much more common. Well, this is the bicarbonate part of sodium bicarbonate. So it's baking soda, sodium salt. What's this one called? Hydrogen phosphate or monohydrogen phosphate ion. This is water. Water turns out to be an acid as well, but it's not a very good acid. So it's way down here at the bottom. But water turns out to be a better acid than these ones down here. Turns out to be a better acid than, what's this called? Hydrogen sulfide or bisulfide. Bi is, used for bisulfide ion or hydrogen sulfide ion. Hydrogen sulfide ion, we must use ion there because H2S is also called hydrogen sulfide, so we want to avoid confusion. This one, ammonia. This one, hydroxide. This is very unusual because hydroxide is considered a powerful base, not an acid, but you know, some things can go both ways. The things that can go both ways, they can act as an acid or they can act as a base. Those are called amphoteric or amphiphilic species. And so if something's amphoteric, it can go both ways. It doesn't mean it goes both ways equally. So for example, hydroxide can be an acid or it can be a powerful base. It's a much, much better base than it is an acid. However, water is very unusual. Water can go both ways, but the reason it's unusual is it doesn't matter. It can go both ways with equal ease. And so it could be an acid, no problem. It could be a base, no problem. In fact, it doesn't really care. Whereas hydroxide would much rather be a base than an acid. Hydrogen is not normally thought of as an acid, nor is methane. So these two are at the bottom of the list. We don't normally think of those as acids. The only way to get those to react like acids would be through very unusual reactions. All right, now on the opposite side we have bases. You know what acids do? Acids lose an H+. So if methane loses an H+, we're left with this guy here. This is CH3-, which is called methide. Methide's very unstable. If hydrogen loses an H+, we're left with hydride. If hydroxide loses an H+, we're left with oxide. If ammonia loses an H+, do you know what we're left with? This one. What did I call this one yesterday? Amide. This is an amide. Here. And then if HS- loses an H+, we're left with, what's this one called? Sulfide. None of these want to lose an H+. If none of these want to lose an H+, that means that these guys are unstable here. And they want an H+. Strong bases really want an H+. So for example, this is called methide. Methide really wants an H+ to form methane. Hydride really wants an H+ to form hydrogen. Oxide really wants an H+ to form hydroxide or even water, 2 H+. Amide really wants an H+ to form ammonia. And so strong bases really have a high attraction for H+. And so we can see this is why we have one chart. They're flipped. The strong acids at the top left here, the strong bases at the bottom right, and that's because they're paired. These pairs are called conjugate pairs. The conjugate pairs is in one direction, it acts as an acid, in the other direction, it acts as the base. And so if we go left to right here, it's acting as acid, we're losing an H+. If we go right to left here, we're gaining an H+, and it's acting as a base. So the strongest bases here, methide is very rare, hydride is very rare. And so we're going to start off with like oxide, amide, sulfide, and hydroxide. These are all the strong bases here. Okay, once we pass hydroxide, then we get to these. The weak bases. And the strongest of the weak bases is phosphate, followed by carbonate, followed by cyanide, ammonia, Phosphoric acid is H3PO4, but this is HPO4, remember 2 minus. So this is an ion, acid anion, called hydrogen phosphate, also known as monohydrogen phosphate because there's dihydrogen phosphate. So this is monohydrogen phosphate followed by hydrogen sulfide ion. Hydrogen carbonate, or a more common name, this is more frequently known as bicarbonate. You know what this is? You know what this is? This is acetic acid, therefore this must be, if acetic acid loses its cation, the anion we're left with is acetate. This is another way of saying acetate. Acetate is C2H3O2 minus. That's the acetate ion. And this is the structural formula for acetate, CH3COO minus. It's acetate. This one is formate. You don't have to have that one known. That's, you go to organic chemistry. You should know this one though. This is fluoride, nitrite. This one you don't need to know. This one you should know. Dihydrogen phosphate, sulfate. If this one is trichloroacetic acid, do you know what this is called? If this is trichloroacetic acid, this is called trichloro. Just work backwards. If we go from the ic acid, the anion is 8. Yeah. This is trichloroacetate. Trichloroacetate forms trichloroacetic acid. This is water. Water is a base. Well, water is both an acid and a base. When something can act either as an acid or a base, we call it amphoteric. A-M-P-H-O-T-E-R-I-C. Amphoteric. Could go either way. There are other amphoteric species as well. Hydrogen sulfide ion, dihydrogen phosphate, monohydrogen phosphate, bisulfate, bicarbonate. Those are all amphoteric species because those species occur on both sides of the chart. If something occurs on both sides of the chart, it's amphoteric. Whereas nitrate's non-amphoteric, it only occurs on the base side. So this is nitrate, nitric acid. This is chlorate, which is chloric acid. This is hydrogen sulfate or bisulfate. And actually that makes sulfuric acid over here because we base the acid names just solely on the base anion. The base anion would be sulfate. That makes sulfuric acid. This is chloride, hydrochloric acid, hydrobromic acid, hydroidic acid, and chlorate, perchlorate, which makes perchloric acid. And so these are the acid-base chart here. But we have to add some details to this. One of the details is, we'll talk about it. We'll talk about it a little bit. This is the strength chart. And it turns out that this is a strength chart. But we know something. The strongest acid here should be perchloric. But there's something funny about this chart. And this is this. in water, all strong acids are equal. Except for H2SO4, which is just a hair stronger. What makes a good acid? What makes a good acid is something that has an H plus that can be given up easily. So that even a weak base can pluck off it. So the way I think about it is, let's take an apple tree. And this will be the HClO4 apple tree. And the apples are the H pluses here. And so a weak, let's say a weak base comes along and takes it. See, the height will indicate the strength of the base, let's say. Because a weak base can easily take those, HClO4. HI, it might be a little harder to take because in HI, you know, some of the H's are a little higher, a little taller. But still, you know, this is it. A weak base comes along to HClO4 and takes the apples. It doesn't have to lift their arm much because all the apples are low, right? And then they go to HI. HI is a little bit weaker, and so that means it's harder to take the H plus. So maybe the weak base has to lift their arm to grab an apple. Lifting their arm is work. You have to lift your arm up and take the apples versus just plucking them down here. But it turns out that if we go all the way to HNO3, okay, then HNO3 still all the apples can be plucked off, but with HNO3, the weak base might have to jump a little bit or stand on their toes, but they can get all the apples, no problem. They'll take all the apples off the tree. Okay, that means the weak base is water. And water can take all the apples off the trees. However, when we get to a weaker acid like phosphoric acid, then water can't reach some of those apples. And so some of the apples are going to be left on the tree. And so we're going to partially pick all the apples. And the weaker the acid, the harder it is to pluck the apples off the tree. And so, you know, when we get to a very weak acid, then a weak base like water can't get those apples. And it's going to have to leave a lot of the apples on the tree because it just can't reach them. And so this is what we say is this, you know, the apples that we generate are hydronium ions or hydrogen ions. And so strong acids like this generate a lot of hydrogen ion in water. Weak acids generate not that much hydrogen. And so the weaker it is, the less hydrogen water gets, hydrogen ions. Water gets. And so in water, it turns out that in water, even though perchloric is easier than nitric is still easy. And so in water, all 7 strong acids are equivalent, are about equal. Therefore, this is called the leveling effect. The leveling effect is, yes, it is easier to pluck the apples off HClO4, but it's still no problem to pluck all of them off HNO3. we start to have trouble plucking all the apples off, the hydrogen ions off, as we get lower. And so HNO2, it's harder to pluck off the H pluses. Water has a harder time to pluck off the H pluses. And so for something like this, for something like HCl, no problem. Water comes along, it plucks all the hydrogens off, and we're left with this. If we go to HNO2, HNO2 comes along, water is going to have a harder time. And therefore, it's not going to pluck all the apples off. And therefore, we're not going to generate as much. And so this is why we showed the double arrow here, because we don't generate as much hydronium. And so the stronger the acid, the more hydronium or hydrogen ions we generate in solution. The 7 strong acids have equal. Now, the strong bases are the same thing. What happens is the strong bases pluck hydrogens off water. And so we're comparing it with water, the acid. Methide, hydride, oxide, amide, sulfide have no problem. They'll pluck all the hydrogens off water. And so if we look at sulfide, for example, over here, sulfide will pluck off all the hydrogens from water. And so we're going to be left with HS minus and OH minus, generate hydroxide. And so the strong bases are equivalent in water except for H2SO4. All 7 strong acids are about equal, except H2SO4. Strong bases are roughly equal, except for oxide. Oxide is going to generate twice as much hydroxide. I wrote the equation yesterday for oxide. And so when we use this chart, the rankings are, this is why we have the border here. The rankings are like this. The strongest acid that can exist in water is hydronium. All these other acids will have been totally plucked clean of their H pluses. The strongest base that can exist in water is hydroxide. No, all these strong bases will pluck hydrogens off water to form hydroxide. All these strong bases pluck hydrogen off hydroxide, hydrogen off water to form hydroxide. Hydroxide is the strongest that can exist in water. All right, great. So we're going to use the acid-base chart to determine. So here, HCl is an acid. Water is an acid. Which one's a stronger acid, HCl or water? HCl. So we're going from a stronger acid to a weaker acid. This is what we call our driving force. Stronger acid to weaker acid. HCl is aqueous. Sodium hydroxide is aqueous. If I have a solution of HCl aqueous, it's a strong electrolyte. Strong electrolytes ionize or hydrolyze completely, so all ionizes completely. Sodium hydroxide. Sodium hydroxide is a soluble salt. Soluble salt ionizes completely into sodium ions and hydroxide ions. Water is it a strong acid? No. Is it a strong base? No. Is it a soluble salt? No. Therefore, it's not a strong electrolyte. Is it a weak acid? Well, in one sense, it is a weak acid. In another sense, do we really think of water as being an acid? No. And so it's not really a weak acid. Weak acids would be up here, above water, but below the strong acids. And these are terribly weak acids. We don't really even consider these acidic. And so from here down. And so it's not, is it a weak base? No. Is it a heavy metal salt? No. And so when we say is water is a non-electrolyte, water is a non-electrolyte, it just stays as is. And the sodium chloride is a strong electrolyte, so that's going to break apart into sodium ions and chloride ions. All these are aqueous, and so what happens is you get tired of writing aqueous, 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 right? We've got to write aqueous so many times. And so as an alternative to that, we could do this. We can leave it blank. If it's aqueous, leave it blank because that's the most common. However, if it's a solid, liquid, or gas, write it in. So water is a liquid, I'm going to write it in. Everything else I'm going to leave blank because it's aqueous. All right, then what didn't react here? Did H plus react? Yes. Did chloride react? No. Did sodium ions react? Hydroxide? Yeah. And so what we do is we just look at the ions that reacted. Hydrogen ions reacted with hydroxide ions to form H2O liquid. And so this would be the net ion equation. And so we can label these. The first equation is the CE, the next equation is the IE, and the last equation is the NIE here. Let's take a look. We got here. They call it the conventional equation. Conventional equation CE. That's what we got. We need the driving force. They didn't put the driving force there. They call it the TIE, but I'm just calling it IE for short. The TIE stands for total ionic equation. That's what we got. And then the net ionic equation eliminates the spectator ions. And this is what we got. Net ionic. It's balanced. All right. Let's do some practice here. Okay, why don't you guys try this one from the lab? This is from lab last week. We have a reaction between hydrochloric acid and sodium carbonate. So what I'd like here is I'd like you to write the CE, IE, NIE plus driving force. Uh-huh. Oh, because here, did anything happen to the sodium? We have sodium ions AQ on the left, we have sodium ions on AQ on the right, and so nothing changed. If nothing changed, then we call it a spectator.
Like as far as the ion charge, or like what changed?
Okay, look at H plus here. We have an H plus on the left. Do we have an H plus on the right? There's no H plus on the right, so something happened. If something happens, then it reacts. Nothing happened to the sodium, and so that's a spectator. The way we visualize it is we have sodium ions in solution at the beginning, we have sodium ions in solution at the end. You know, we could draw, you want me to draw out the beakers, we could do that. So if I were to look at the beakers, the CE is this. The CE is what you label the beaker. So in one beaker we have HCl. HCl consists of H plus and Cl minus. And so this is the IE. The IE is what's inside. The CE is how it's labeled. So the beaker is going to be labeled HCl. Inside we have H plus and Cl minus. Over here the beaker is going to be labeled NaOH. Inside here we're going to have Na plus and OH minus. And then let's mix them together. When we mix them together, the favorable ion combination is H plus and OH minus. H plus and OH minus likes to form H2O liquid. And so we're going to get H2O liquid. But what happened to the sodium ions? Nothing. The sodium ions are still there. What happened to the chloride ions? Nothing. Chloride ions, they don't react. They're still floating around in there. Well, the sodium and the chlorides are floating around in there. We're just going to label it NaCl, aqueous, like that. And so we have chloride ions there at the beginning, floating around. We have chloride ions at the end. They're just doing nothing, floating around in solution. That's it. So it's called a spectator. We have sodium ions floating around at the beginning. We have sodium ions floating around at the end. Those are spectators. And so in an NIE, we're just looking at what ion combination, what ions like to react. Well, hydrogen ions and hydroxide ions react to form H2O liquid. And so the CE's this, what the beakers are labeled. The IE's what's inside the beakers, and the NIE's just looking at the ion combination that likes to react. Okay, so the reaction, did I write the reaction or did I just erase that? All right, for practice, let's do this one. Why don't you work on this one? This is from our lab last week. Hydrochloric acid plus sodium carbonate. Hydrochloric acid plus sodium carbonate. That A is for practice. D, sulfuric acid plus potassium carbonate. We're just going to do some select reactions from the lab. Barium chloride plus ammonium sulfate. Barium chloride plus potassium carbonate. Wow. Let's just go with these three for right now. We don't have that much time.